This problem for special relativity reads: a Klingon spacecraft has a speed of 0.75 times the speed of light with respect to the Earth. The Klingons measure 37.0 hours for the time interval between two events on the Earth. What value for the time interval would they measure if their ship had a speed of 0.94 times the speed of light with respect to the Earth? So the Klingon spacecraft is moving at the speed here, but it says in the problem that the Klingons measure 37.0 hours for the time interval between two events on Earth. That means we have to look at the problem from the perspective of the Klingons, which means for them we have to look at the reference frame of Earth, and for them that one is the one moving. So let's see, I'm going to flip this around there. Oops, at least I tried flipping it around. There we go, maybe that worked. There we go. And so for them, because the different frames of references have equal validity, as if the Klingons are looking at the Earth moving away from them. And so that means for them it's the time dilation happening on Earth, and I'm going to write the equation down for the time dilation. So here's the one for the Earth, the time for the Earth, and that equals the time for the Klingons on their spaceship. That was the symbol for Earth, circle with a plus sign inside, 1 minus v squared over c squared. And that was supposed to be a k here. Okay, well this one here is the 37.0 hours that they measure for the Earth between two events. And that one, from their point of view, is the speed with which the Earth moves with respect to them. Not necessarily away, they don't say that, but with respect to them. So which means with this one here I will be able to determine how much time expires on the Klingon spaceship. Since this is time dilation, the time that they measure for what's happening on Earth is going to be longer than their own time that they measure on their ship. And that's what I'll be calculating here. I know that's not what it's asking for, but the thing is, after that they're going to change this number here to 0.94, and I have to do basically the same calculation again. So let me calculate this one. So I need to do a couple of things. Of course, the algebra, get the square root on the left hand side, so multiply with that square root or the inverse of the gamma factor, and then technically I would have to put in here 300,000 kilometers per second, and here I would have to do 3/4 of that, which is 225,000 kilometers per second. But if this one is already in terms of the speed of light, then I have the speed of light squared up here divided by speed of light, which means that speed of light squared, which means it divides itself out, and it's pretty much just 0.75 squared divided by 1 squared. I'll show you that on the calculator. Okay, so it's the 37.0 hours times the square root of, so get the square root to the other side, 1 minus, and here's the 0.75 squared, divide c times c squared, divide by 1 c squared, but as I said, those c squareds divide out, so that's the reason why I can write it this way. So whenever you see the velocity in terms of c, just use the fraction for that. And there we go. So that means that the time on the spaceship that expires is 24.5 hours. And that's what I had mentioned earlier, because they see the time dilation happening for Earth. They measure 24.5 hours, while for them on Earth 37.0 hours expire. Okay, then they're changing the numbers from 0.75 to 0.94 c. And again, from their point of view, that's how fast the Earth is moving. So now it's going to change to the time dilated time on Earth divided by the Klingon time. I'm sorry, not divided by, but equals the Klingon time divided by the square root of 1 over v squared c squared. Take the square root, and now this one right here is 24.5 hours, and this one down here, that's the 0.94 times the speed of light, and then just plug in numbers and you'll come up with something in hours. And the Klingon time is 24.5 hours. They measure the time dilation on Earth, so it has to be a longer time, and because the speed now is quite a bit closer to the speed of light, that time should be quite a bit more than 37 hours that we had, that was given in the problem. This problem reads, an astronaut traveled at a speed of 7,800 meters per second relative to the Earth, a speed that is very small compared to the speed of light. According to a clock on the Earth, the trip lasts 15 days. Determine the difference in seconds between the time recorded by the Earth clock and the astronaut's clock. Hint, when the velocity is much smaller than the speed of light, the following approximation is valid, and that is that the square root of 1 over v squared over c squared equals 1 minus 1/2 v squared over c squared. Okay, I'm going to first set up the problem. So I have the time on the space shuttle, I guess. Astronaut travels on, doesn't say what the astronaut is on, but let's say it's the International Space Station, ISS, and that's perhaps what this astronaut is working on. I believe I got this image from, I think I googled astronaut free image or something like that. Oh no, I got it from the Microsoft Word text program, so I figured it's a free image because they had it on there. Okay, anyway, so the time on the International Space Station equals the time on Earth divided by 1 over v squared c squared square root. And the time dilation happens here. That means that this one here is the exact 15 days. So times 24 hours times, yeah, I'm just going to write d there, times 60 minutes times 60 seconds. We'll do that in a moment. And then the time here on Earth is whatever that time is, and we're supposed to figure out what the difference is between the two. That also means, and then here, the v here is the 7,800 meters per second, and of course in this case I have to plug in here the 3.00 times 10 to the 8 meters per second, yeah. 3.00 times 10 to the 8th meters per second for the speed of light. In this case, since this one is given in meters per second, I have to do the same thing for the speed of light. I cannot take the shortcut of dividing out c squared because this one is not given in terms of c. Alright, this is, I have to figure out what the time difference is, so this is what I would have to do. The following algebra, which is that TISS, which is the 15 days, respectively, whatever that is, times 24 times 60 times 60. Didn't mean to put a equal sign there, but the square root 1 minus v squared c squared. And that gives me the time that has expired on Earth, which is just a little bit shorter. Just a little bit shorter than 15 days. And then I'll determine the difference between this one and this one. Okay, they give us a hint here that we should use the following approximation because velocity is so much smaller than the speed of light, and we can see this one is in the thousands while this one is the hundreds of millions, and that means we have a difference of like 5 powers in between, and then that's being actually squared, so we have kind of a difference of 10 powers in between, and usually calculators cannot handle that. That's why they give us that approximation. But I'm actually going to show you first that typically graphing calculators can do that. So here it is. I'm going to plug in, well, first actually I'm going to do 15 days times 24 hours times 60 minutes times 60 seconds. So that's 1,296,000 seconds. So 1,296,000 multiply by the square root of 1 minus, and so I'm using the normal gamma factor, and then divide that by the 3.00, the speed of light, 10 to the 8th squared, and put another square there. So I'm actually not going to use the hint, but watch what happens when I do that. I come up with basically the same, well, I come up with the same result. However, what's happening here is that this number here is just going to be a tiny bit smaller, but it's way back here. It's way a decimal back there. So what I'm going to do is I actually subtract the 1,296,000 from that and see what the difference actually is. It just doesn't show here because it's such a tiny difference. And there it is indeed. 4.4 times 10 to the negative 4 seconds, so kind of like half a millisecond. We could say that the astronaut on the spaceship after 15 days is half a millisecond younger than somebody on Earth. So for those small speeds, the special relativity is virtually negligible, at least as far as the astronaut is concerned. It actually, even that tiny difference does make a difference to things like global positioning system, which are basically in similar orbits very close to Earth as what the International Space Station is. And for those global positioning systems, you really want to have high accuracy. They're supposed to give you your location within just a few feet, and imagine a few feet compared to thousands of miles. Well, they have to have a very high accuracy, so they have to rely actually on special relativity, even though the difference is very tiny. In any case, I showed you the proper way of calculating it, but if you use a different calculator, then the approximation is going to kick in. So let me do the approximation, which is pretty much saying that we should be writing square root of 1 minus v squared c squared. So here this one is the approximation. That one is virtually the same as 1 minus, it says in the hint, 1/2 v squared over c squared for the velocity much less than c. Okay, if I plug this one onto the calculator, I really just come up with 1 again, because that difference is so tiny. So what I do instead is, when I type this onto the calculator, I'm just going to do this part back here. And if you can imagine that this whole thing is supposed to be multiplied with the, what was that, 1,296,000 seconds anyway, and then it's supposed to be a difference, which means I have to subtract the 1,296,000 seconds. Then that would mean, as I do that, times, what was it again, 1,296,000 seconds. And then I have to subtract that from that because I'm supposed to come up with a time difference. Well, if you look at the algebra, it's pretty much that the one out here subtract itself out, and it's basically 1/2 times v squared over c squared times that time here, the 1,296,000 seconds. And that one, any kind of calculator can handle because there's not this subtract a tiny, tiny difference from 1, which is going to give you like in the 10th decimal or something. But here it's pretty much, well, multiply, multiply, divide, and so on. And yeah, you're going to come up with a small number, but any kind of calculator can handle that. Okay, so let me do that. It's going to be 0.5 times 7,800 squared divided by 3 times 10 to the 8th squared times the 1,296,000 seconds. And indeed it's the exact same answer, and I guess earlier I subtracted the other way, that's why I came up with a negative. But this one here means 4.38 times 10 to the negative 4 seconds is the time difference, and that's by how much younger the astronaut is as compared to somebody on Earth. Respectively, that's by how much more this time is compared to this time. But that, of course, is the time that we measured for the astronaut, while, of course, from her point of view, that's how much younger she is. This problem reads, the distance from Earth to the center of our galaxy is about 23,000 light years, as measured by an Earth-based observer. A spaceship is to make this journey at a speed of 0.9990 times the speed of light. According to a clock on board the spaceship, how long will it take to make the trip? Express your answer in years. All right, so I took an image here of a barred spiral galaxy because that's how our Milky Way galaxy looks like, and then we might be here in one of the spiral arms, actually maybe here, and then here's our spaceship that's supposed to fly from here to there, and that's just the illustration. And the distance here, let me actually make this smaller overall because I will need the space. So we're supposed to fly this distance here, there, and that would be the 23,000 light years. And because they give us a distance, that would mean we would have to use the length contraction. So that's what would be called the L0. Okay, for us on the spaceship, it's not going to be 23,000 light years, but because we fly with that really high velocity, very close to the speed of light, that one is going to look a lot shorter to us. So it's going to be L equals L0 times the square root of 1 over v squared divided by c squared. And yeah, of course, this one here is the 23,000 light years, and this one here is the 0.9990 times the speed of light. And again, when I plug this in here, the c squareds are going to divide out, and I basically subtract 0.9990 squared. Okay, I'm going to do the calculations here in a moment. They give some extra numbers in here. They say that a light year is 9.47 times 10 to the 15 meters, and that a year is 31,600,000 seconds. I'll see if I actually need that. Let me just show you how they came up with the first number. The second number is simply multiply 365 times 24 times 60 times 60. in order to come up with the number of seconds in a year, but the first one is the light year, which is 3.00 times 10 to the 8th meters per second times, and then actually here's the year, 365.25 times 24 times 60 times 60, and that comes up with the number they give, 9.47 times 10 to the 15 kilometers. So the light year is a distance, not, as some may assume, a measure of time, but a measure of distance. That is the distance that light would traverse in 1 year. 9.47 times 10 to the 15 meters. If I said kilometers here half a minute ago, no, it's in meters, which is about 9.5, let's see, trillion kilometers. Now I got it right. Or in the neighborhood of 6 trillion miles. And in comparison, our solar system is about 1 billion light years across. Maybe it's actually, I take that back. It's about 6 billion miles across. So light traverses 1,000 times the distance of the diameter of the solar system in comparison. Anyway, that's where they got the number from, and as I said, I may actually not need it. I'll see here what happens in a moment. So first I'm going to calculate how far the distance actually is from our spaceship's point of view. So 23,000 light years times, and here comes the length contraction, 1 minus, and then there's the 0.9990 squared, and because the c squareds divide out, I don't need to write anything down there, and I come up with 1028 light years, and that is the distance in light years. If I divide that now by the speed of my spacecraft, and let's assume that my spacecraft was going actually at the speed of light. Of course it can't, but let's assume I would simply divide by 1. I would come up with 1028 years. However, it is not going at the speed of light, but at 0.9990, and I think you can already see what's happening. It really didn't increase the time here a whole lot, so I divided by my speed of 0.9990 speed of light, and I come up with 1029 years, or around it 1000 years, because it's supposed to be two significant figures. So in order to get to the center of the galaxy, it would take me 1000 years in order to traverse a distance of 23,000 light years. And even though I'm not going to write the number down, what I should write down is the time that it takes me is going to be that distance L, the 1028 light years, divided by my speed. And as you see, if I stay in units of c, I arrive just as well as the answer of 1000 years rounded, as if I converted everything to meters per second.